So ionic compounds, ionic bonds involve transferring of electrons. The metal transfers electrons to the nonmetal. Metals have lower ionization energy than nonmetals do. So it's easier for them to lose electrons, and then the nonmetal gains an electron. So in Lewis theory, we represent this by moving electron dots from the metal to the nonmetal. So let's look at what happens with potassium and chlorine. So potassium is K, and how many valence electrons does it have? One. And chlorine, Cl, how many valence electrons does chlorine have? 7. 1, 2, 3, 4, 5, 6, 7. So we're going to think in terms of them wanting to have 8 valence electrons. So chlorine is thinking, if I could just get one more, my valence shell here would be full, I'd have an octet, I'd just be so happy. And potassium is thinking, I've got this one extra one, I just need to ditch it. And so chlorine says, well, I'd be happy to take that off your hands for you. So that electron moves from potassium to chlorine. The result now is that chlorine has a charge, a -1 charge, and potassium has a +1 charge. Opposites attract. And so these guys are going to stick together like magnets.
So that's what chlorine has.
Pardon me?
Can you just say, like, that's what chlorine is negative?
Yes. That's why chlorine makes a -1 ion, because by gaining one electron, it gets this beautiful octet. Now you might say, well, it doesn't look like potassium has an octet. He looks kind of naked over there. Well, let's look at potassium's electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So this is the electron configuration for potassium. If we get rid of this one electron, what do we have down here? How many valence electrons now? 8. So we took off this extra little tiny bit, and underneath is this nice full shell. Okay? We don't suddenly put all those dots in there because that would be confusing. We understand that if an atom loses all of its valence electrons, what's underneath is 8 valence electrons. Any questions? The chloride has an octet. The potassium lost its only valence electron. It's left with an octet in the previous shell. I showed you that. The Lewis structure of the anion is usually written within brackets and the charge put on the outside. So that's what I did with chlorine here. You can kind of imagine how a negative sign might get lost in the dots, especially with handwriting, right? So we put brackets around the Lewis structure, all the dots and the symbol, and we put the charge on the outside. Mastering chemistry can't handle that. Really? Yeah, really. So in mastering chemistry, the charges are shown, but the brackets are not shown. There is no bracket tool. I'm sorry. I would do it differently, but it's not my job. So please don't text me and ask me how do you do the brackets. You can't do the brackets. But when you're writing with your hand, you can do the brackets. Let's write the Lewis structure for the compound sodium bromide. I'll start with sodium. How many valence electrons does sodium have? 1. And then let's look at bromine. How many valence electrons? 7. It's in group 7. So we're looking at this picture and we're trying to get 8 valence electrons for everybody. So if sodium gives this electron to bromine, Then bromine will have 8. Sodium has cleared out this incomplete level, and underneath he's got 8 valence electrons. So we're going to move this one, just take it away, and put it over here. That gives sodium a positive charge and bromine a negative charge. And so the Lewis structure for an ionic compound is just those two sitting next to each other. So Lewis structures help us to understand how ions form, but we don't often draw Lewis structures for ionic compounds. It's more of a explaining, learning sort of thing. We do it a lot more for covalent compounds. Let's look at BAF2 and see how Lewis structure can predict the formulas. So barium has how many valence electrons? 2. And so here's, we'll put fluorine over here, and fluorine's in group 7. It's got 7 valence electrons. So fluorine's saying, hey barium, give me one of those electrons. And barium's like, fine, I'd be happy to get rid of this electron. I'm trying to get rid of 2 of them. Do you want the other one? Fluorine says, nope, I'm good now. So fluorine has a negative charge now. Barium has a positive charge. Is everybody happy? No, barium's not happy. He's still got this extra electron. What does he do? Well, if there's one fluorine hanging around, there's probably another one. So he's going to find another fluorine atom. So here's another fluorine atom with 7 valence electrons. And he's like, hey, I'll give you this electron. And fluorine says, awesome, I would love that. Can't believe I do this. Can't believe they pay me to do this. So barium had 2 valence electrons. It lost both of them. Gave one to this fluorine, one to that fluorine, making both of these -1 ions with 8 valence electrons. Now we've got positive charges and negative charges. They're all attracted to each other. And this represents barium fluoride. Any questions? Let's look at magnesium and nitrogen. So magnesium has 2 valence electrons. How many does nitrogen have? 5. Wake up. Now, if you have struggled with putting ions of different charges together, this might help you to understand what's going on. So nitrogen has 5 valence electrons, magnesium has 2. Magnesium wants to get rid of these 2. The only other way magnesium could become happy with 8 valence electrons, it would have to gain 6. Gain 6, lose 2. Losing 2 is easier. And for nitrogen, it would either have to lose 5 or gain 3. Gaining 3 is easier, it's closer. So nitrogen is begging magnesium for those valence electrons. And magnesium is very happy to get rid of them. So we take this one, and we give it to nitrogen. And I'm going to take this one and give it to nitrogen. Now what has that done to the magnesium? It gave it a charge. It's a 2 positive charge because it lost 2 negative charges. Is this magnesium ion happy? Yeah, it's happy. Is the nitrogen happy? Not quite. Closer. But close only counts in hand shoes and horse grenades. Horseshoes and hand grenades. What would a horse grenade look like? Sorry. Okay. 2 minus charge. Not happy. So what's the nitrogen going to do? Look for magnesium. So here's another magnesium, 2 valence electrons. Nitrogen says, hey, give me that one. Magnesium's fine, you can have it. So there. That changes the charge, so this is now 3 minus. And this magnesium is going to have a +1 charge. This magnesium's happy, the nitrogen's happy, this magnesium not so much. What do? Bring in another nitrogen. Nitrogen has 5 valence electrons. So the magnesium is able to give this electron to the nitrogen. This is the point where you think this is going to go on forever. So now we've got 2 happy magnesium ions, 1 happy nitrogen ion, and 1 not so happy nitrogen ion. So this has a -1 charge. What to do? Bring in another magnesium, right? It will. So here's magnesium. So magnesium donates 1 electron. Take this electron off, give it to the nitrogen. Nitrogen says, well, that was awesome, but could I have the other one too? And magnesium's like, yeah, here you go. So now, this nitrogen has a 3 minus charge, this magnesium has a 2 positive charge. It took this was the smallest combination of magnesium and nitrogen atoms that could get together and transfer electrons so that they can all have an octet. To write the formula, you count up how many there are. There's magnesium, 1, 2, 3. Mg3. And there's 2 nitrogens, N2. We learned to do the formula a different way. We learned to predict by position on the periodic table that magnesium is a 2+ ion and nitrogen is a 3- ion, and we either thought about it or we did the crisscross thing, and we ended up with the same thing. But this shows in really quite a simple form what's happening. Any questions?